Yeah, thank you, Igor. Yeah, we have probably about an hour or so, so let's see what we can cover. So I'll go faster than before. You can see how many activations you can fit in a given time interval that way. It's all about that in the end. It is activations, right? Your brain neurons are getting activated, basically. That's how it works. Okay, so this is actually the longest part, low latency memory. The other parts 5 and 6 are shorter. So maybe I'll give you a short overview of low latency memory, and then we're going to finish with the other two parts. The last part is actually easy because it's on principles mostly. Okay, so let's start. As I said, latency is important and it's not reducing as much, but I think latency is extremely important if you want to solve the hardest problems. They're all latency bound in the end. I mean, we may spend a lot of time on bandwidth and energy, but how quickly you can reach the results is really important, and that's really all about latency in the end. And if I have to make a joke over here, I'll basically say everything over here is about speed in the end. Sometimes if you're fast enough, you don't need enough energy, or more than some energy. Okay, the key question is, how do we design fundamentally low latency computing architectures? And as I showed you, we're not doing too well. But before I go into it, let me outline some properties of data-centric architectures. I think data-centric system design is a different principle than processor-centric. First of all, we want to process data where it's writes. We want to minimize data movement. But also, I think it's important to respect the data in the sense that we really want to enable low latency and low energy access to the data. I think if you're data-centric, you have to really prioritize the data more than anything else. And that also requires low-cost data storage and processing and intelligent data management. I'm not going to talk about these two. But let's talk about this low latency and low energy access. I think low latency, I'm not going to talk as much about energy here. I mean, reducing the data moment clearly reduces energy, but also reducing the latency as well reduces energy because you're not activating the structures for long. So reducing latency is good for a lot of things. Let's start with this. So as I showed you, main memory latency lags behind. We have not improved memory latency as much. And in fact, some latencies are increasing. The Samsung and Intel paper, this is based on some work that we've done. The Samsung and Intel paper that I mentioned says write latencies are going to increase. But latency is critical for performance for many applications because it leads to performance quality. This is actually a paper that we wrote very recently in June. It was published at Symmetrics in June. In this paper, we actually studied a large number of workloads, 6 different classes and 9 different DRAM types. And we showed that new DRAM types make the following trade-off. They improve parallelism, like bandwidth, but they increase latency. And when you make that trade-off, applications actually don't do well. There are a lot of applications who lose performance because of these new DRAM types. And this paper actually documents a lot of them. And we release a lot of the source code so you can find and do the study similarly yourself. I think there should be more studies like this going into the future. Okay, let me give you the high-level perspective. Basically, clearly memory latency is a significant limiter of performance and energy efficiency. And it's becoming increasingly so with higher memory contention, multi-core and heterogeneous systems. These systems have more contention memory, and latency, large latencies exacerbate the bandwidth need and makes the quality of service problem worse. And it also increases the processor design complexity, as we discussed, because you have many mechanisms to tolerate memory latency. I'll give you some historical perspective. So since we don't have a lot of time, I'm not going to go into a lot of detail in some of the techniques, but I think this historical perspective is important. So this is a slide that I prepared in 2003. This may be the oldest slide in these presentations. This is from my PhD thesis proposal. As I mentioned earlier, I worked on memory latency tolerance techniques, developed something called run-ahead execution. And in all PhD proposals, it's a good idea to have a related work slide, at least one, and this was my major related work slide. Basically, we were looking at conventional latency tolerance techniques, caching, prefetching, multi-threading, out-of-order execution, and they're all fundamental. They were all developed in the 1960s, and people have innovated on them a lot over the years. We all employ them. Now, I motivated this saying that out-of-order execution is a good technique, and we need to make it much more. This tolerates cache misses that cannot be prefetched, for example, because you're really overlapping the latencies. And we want to develop mechanisms that are fundamentally simpler to get those benefits. That was my motivation at that time. It was still the processor-centric viewpoint, meaning we wanted to improve the processors. But if you go back and look at it at this point in time, I would say none of these fundamentally reduce memory latency. Basically, all of these are there: caching, prefetching, multi-threading, out-of-order execution. They're either tolerating the memory latency or reducing the memory latency from the processor's perspective. The memory latency is there. and you put it into a cache so that the processor has fast access. But the first time you pay the latency. Prefetching pays the latency for the first time you build it, you bring the data into the cache or prefetch buffers. Multi-threading out-of-order execution don't reduce the latency at all. They basically tolerate the latencies. So essentially, these are processor-centric perspectives. They're actually good. I think these ideas are good to be examined from the data-centric perspective at some point also. But our goal was to actually reduce the latency. So let me give you an idea of what I did for my PhD thesis, because it's always good to be proud of your own PhD thesis all the time. And I'm proud of it. I like it. It's a different world, though, in a sense. I moved on to other stuff after that. So basically, the idea of run-ahead execution is very simple. It's a processor-centric viewpoint, and I think we need simple ideas like this. So basically, ideally, from a processor-centric perspective, you want minimal latency, meaning perfect caches, right? If you can cache everything nicely, everything hits in the caches, and you get all green execution. But if you have an out-of-order execution engine that's aggressive, usually you end up with a small instruction window. You have small look-ahead because the structures are complex. So what happens in an engine is you basically get to a cache miss, and while the cache miss is happening, the processor processes some instructions. It can do limited out-of-order execution. And at some point, its buffers become full. Once its buffers become full, the processor stalls. And then the cache miss comes back, the processor starts computing again, and then it gets to another cache miss, and the same thing happens. Basically, most of the cycles are dominated by these red parts, which you've seen in the results that we've seen earlier, right? Google's results, my results, and also Dick Site's results. Okay, my goal in my PhD, our goal in my PhD was to actually do something useful during these times. And the idea is run-ahead execution. It's a very simple idea. It's actually simple to design as well. It touches some parts of the processor. Basically, when you get to long latency cache miss, soon after that, this cache miss becomes the oldest instruction in the window. That's the oldest in the machine. At that point in time, you say that, oh, I'm going to wait for a long time for this cache miss to return, so why don't I do something useful instead? And what is that useful thing? You enter a mode called run-ahead mode. In this run-ahead mode, the processor keeps executing instructions, but it does so speculatively. Basically, it runs out of buffers, but drops the instructions out of its instruction window. So why does it do that? Because it checkpoints the architectural state when it enters the run-ahead mode so that it can go back to it. So it takes a checkpoint, starts speculative processing, speculatively executes instructions, and at the end of the run-ahead mode, it's going to go back to the checkpoint. Now, what's going to happen in the run-ahead mode is because you're speculatively executing instructions, hopefully you'll get to this second load miss and start generating the memory access early, and you'll overlap the latency of this cache miss with the latency of the cache miss that caused entry into the run-ahead mode. That's the idea. Of course, this happens if you can get to it, and also if this load miss is independent of the first load miss. But we've also looked at methods for parallelizing dependent cache misses as well. So basically, at the end of the run-ahead mode, when this load miss comes back, you flush the pipeline, restore the checkpoint, start from re-executing load 1, you re-execute load 1, and re-execute a bunch of stuff, and at some point the second miss completes. But when you re-execute load 2, now it's a hit in the cache, so you don't need to stall for it. So you save a bunch of cycles. That's the idea with the run-ahead execution. It's a processor-centric way of reducing memory latency by parallelizing cache misses, as opposed to stalling and doing nothing during that time. Yes?
So it doesn't matter if, it's not about computing, but it's just reaching the point where you will need again a value from the memory, and then...
Absolutely. That's the benefit, basically. The benefit really comes from prefetching. We also examined, can you reuse some of the results that you actually generate during this time? You don't get a lot of benefit out of that, actually. You can reuse some of the branch predictions also. There are a lot of policies we examined. If you're interested, you can take a look at the works. It's fascinating, I think. I'm still fascinated by it, even though it's been more than 13 years now. Okay, but basically, this is an idea that works. I like this idea. This is a very processor-centric idea, and people implemented this idea. This is a slide that I use. This is from Sun. Sun was developing, working on this idea when they existed in their Sun Rock processor. They've written papers on it also, but I like this one because it's very clean. It's from a presentation that they delivered in 2008. They called it Scout threading, not run. We call it run-ahead execution, but it's essentially the same thing. Scout goes forward and finds out the problems, right? This machine goes forward and finds out the cache misses, and they basically show that at this point of operation you get 40% better performance, or you can use run-ahead execution to reduce your cache size, right, significantly. And they show this on online transaction processing workloads, for example, that they were designing machines on. So I like this sort of simple ideas because it reduces complexity and enables better performance and efficiency at the same time. So if you're interested, this is the first paper I wrote, and We've written a bunch of papers related to this to solve some of the problems that clearly this is executing a lot of instructions. How do you reduce the execution of those instructions is one problem. But we also looked at a lot of wrong path effects, because sometimes when you go into this run-ahead mode, you spend a lot of time in the wrong path. How do you reduce that wrong path? So these are old papers. Okay, so I should probably add run-ahead execution over there. That also doesn't fundamentally reduce latency in the end, right? These all are good ideas, but none of them are actually doing, in a sense, the fundamental thing to get rid of latency. So we want to get rid of latency. How do we do that? So I think you need to realize the problem first. First problem is modern DRAM is not designed for low latency. Main focus is cost per bit. We discussed this before. And the second is modern DRAM is determined by worst case conditions and worst case devices. Latency is determined. So much of memory latency is really unnecessary. There's a lot of timing margin that we put into this based on operating conditions as well as process variation that you get across the devices and within the device as well. So I'm going to cover this one. This one I don't think we will have time for. You can look at the slides, but basically you can trade off between latency and capacity better to get to a better point in terms of reduced latencies. So basically we want to reduce the memory latency at the source of the problem. So basically we realize this and we want to tackle the design of the DRAM microarchitecture to minimize latency somehow, and we want to get rid of this one-size-fits-all approach to latency specification. So basically today we're using same latency parameters for all temperatures, all DRAM chips, all parts of a DRAM chip, all supply voltage levels, and all application data. So ignore the application data. Application data requires maybe understanding of your data. But you can actually make latency parameters more heterogeneous or different across these different conditions. That's the key idea over here. And this is a relatively low-cost approach. I call this tackling the fixed latency mindset. Basically, we have very heterogeneous latencies. So why don't we somehow figure out and use the lowest latency one can reliably access a memory location with? So I'm going to give you a couple of ideas here. Adaptive latency DRAM will be one. And then it's going to be static, not even dynamic. And then we develop more dynamic mechanisms to take advantage of the latency heterogeneity. And then we started trading off between voltage and latency to improve energy efficiency. And then actually, once you start thinking latency is variable, it enables a lot of things. So we, for example, figured out once you reduce the latencies, some particular DRAM cells start failing. And that failure is a fingerprint of the device. So it's really a physical unclonable function. And this is a very reliable physically unclonable function. We also figured out that some other cells randomly fail, meaning 50% of the time they fail, 50% of the time they don't fail. Essentially, you can use that cell as a random number generator bit. And since DRAM exists in pretty much all devices, with some changes to your memory controller, you have a very nice high throughput, low latency random number generator by reducing the latency parameters. That's the idea. So we won't talk about those, unfortunately. We won't have time. I think these are fascinating. There's more to come, I think, that we will see. Actually, there's a paper that's coming up at Micro. I mentioned this paper. This paper showed that you could do row clone on existing DRAM just by modifying the latency parameters, by reducing the latency parameters. They also showed that in some limited set of DRAM chips, you can get results very similar to AND-bit. Basically, you can do AND and OR. And these are real DRAM chips by fudging the latency parameters such that you get the effect of triple row activation. So they changed the latency parameters using the soft MC infrastructure that we discussed. They built on it, and they basically showed that if you reduce the latencies nicely, you can get bitwise AND and bitwise OR, just like we predicted with AND-bit. Of course, it's not as reliable because the DRAM is not designed for that purpose, but it shows that you can do it in existing DRAM chips. I think this is very fascinating. But I think all comes from the getting rid of the fixed latency mindset. Latencies are variable, and you can first reduce the latency and minimize it, and you can create other benefits if you actually know how to reduce these latencies, like generate random numbers, generate physical unclonable functions, and do some computation capability or cloning capability. Okay, let me talk about how do you reduce the latency. Basically, the problem is you have heterogeneous manufacturing and operating conditions, so you have latency variation. So DRAM latency looks like this, really. This is true DRAM latency, which is the latency that's needed to reliably access a memory location with. And that looks like this. So there's some slow cells and there's some weak cells in a DRAM chip. So essentially, DRAM latency is specified in the data sheets in the DRAM standard. This doesn't reflect the true DRAM device latency because of imperfect process variations. You get latency variation. So what do we do today? Basically, different DRAM chips have different latencies. Within DRAM chips, you have different latencies. So the data sheets set the standard latency very high. Why? Because they want to make sure all of these devices are acceptable. So this is what maximizes yield in when you manufacture all these chips, and they have very different latency characteristics. You choose the standard latency as high as possible so that all of them are acceptable. Your yield is maximal, but your latencies are not very high, right? That's the idea. So we want to get rid of these timing margins. Basically, you have a timing margin problem. Timing parameters are set to cover the worst case. So it's also worst case temperatures, basically. DRAM is specified to operate at 85 degrees, but the common case is not 85 degrees. I'm going to show you some results in a little bit. Common case is, let's say, 50 degrees or 45 degrees. So, but the latency is specified at 85 degrees. At 85 degrees, you have a lot of leakage. As a result, circuits, you don't have enough charge, and because you don't have enough charge, you don't have enough drive, and you need to wait much longer to ensure that the charge drives the sensing circuitry, for example, to be reliable. Whereas at smaller temperatures, lower temperatures, you have a lot of charge in the cells, and you don't need to wait as much, because that charge goes relatively fast and enables the sensing structures quickly, so your latencies can be lower if you want reliable operation. Okay, also worst case devices, I've already talked about it. Basically, you want DRAM cell with smallest charge across any acceptable device, because we want to maximize yield, right? So as a result, this worst case mindset leads to large timing margins for the common case. So basically that's what we wanted to do. We wanted to understand how bad are these timing margins in DRAM. And we had this infrastructure we built for other reasons, clearly, and we use the infrastructure to reduce the latencies and look at when we are getting errors and how often we are getting errors and where we are getting errors. That's exactly what we did. And you know that you can do all of these studies yourself because it's all open source. So, we developed this idea based on what we observed. The idea is very simple. It's called adaptive latency DRAM. We want to optimize DRAM timing parameters online. And in this case, we don't determine the timing parameters dynamically. Somebody gives them to you. Somebody says there are, let's say, 2 sets of timing parameters for a given DRAM chip. One is the current set of timing parameters, 85 degrees Celsius for this chip. The other one is, if you're operating at lower than 55 degrees Celsius, these are the timing parameters that you use. These are faster timing parameters, clearly. And somebody gives them to you, DRAM manufacturer in this case, we said. And the system monitors the DRAM temperature and figures out which timing parameter to use. So of course, you need to monitor the DRAM temperature. This already exists in existing chips. And somebody needs to figure out the reliable timing parameters. I think manufacturers can do it, but also system designers can do it. How many of you are hardcore gamers here? You've got to be hardcore. Okay, if you're hardcore, have you reduced your timing parameters in DRAM? Maybe, okay, it's the next thing to try tomorrow. Basically, a lot of hardcore gamers actually increase the frequencies. They actually overclock a lot of their systems, but some of them also reduce the timing parameters of DRAM. They don't do it reliably in general, because they say, okay, I'm not getting errors, so everything is good. And they're happy. When they get errors, I guess they get pissed off, but that's fine. Usually they don't get errors. But I think we want to do this reliably, and we actually have methodologies for doing it reliably. And it's not that hard, in my opinion. But I'll give you the basic ideas. So with our infrastructure, we examined almost 1,000 chips, DRAM chips, in 2014 or so. And these are the latency reductions that you would get on average for a read or write if you're operating at 55 degrees Celsius, if you customize the latency for that particular chip. It's basically significant. It's more than 30% reduction in read latency, more than 50% reduction in write latency. And this is average. Some chips see larger reductions, some chips see less reductions, clearly. And there's a lot more analysis in the paper that I'm not going to go through. And the paper has a lot of different types of analyses looking at the refresh versus latencies as well. So if you actually profile your DRAM chip and figure out the reliable latencies to operate it with, and if you do that on a real system, you get significant benefit. And we did that on a real system. Unfortunately, real systems, at least what is exposed to the users today, you cannot change the latencies dynamically while the system is operating. You can change them at the BIOS level in some systems. So this is an AMD system, for example. And if you go through the BIOS specification, it says that you can change some of the latencies, like the row activation and pre-charge times. So we did exactly that. We knew what parameters were reliable for a chip that was operating below 55 degrees Celsius. We changed the parameters, and we ran a bunch of applications on that system, and we got pretty good results. I mean, you could get better results, but these are the results we got. If this is single core performance improvements, you get more than 6% on memory intensive workloads. And if you have more intensive workloads, like multiple workloads accessing memory at the same time, you get about 14% performance improvement. And these are real system results. You can read the paper. Of course, what we envision is doing this dynamically, not just statically changing in the BIOS in the end. And I don't think it's really that hard once you have a good memory controller to be able to do that. So the benefits are real in the end. Maybe there are other benefits. In the end, we didn't really explore the full potential of it, I think. And also, we showed that you can reduce the power consumption. Reducing latency is good for other stuff, as we've discussed. It reduces complexity, but it also reduces power consumption because you're not activating things as much. Okay, so let me give you quickly advanced and disadvantaged. This part 4 is actually structured like a lecture where you go through advanced and disadvantaged of everything and then build up to better stuff, but I don't think we're going to cover a lot of things. So this is a very simple mechanism to reduce latency actually. It provides significant system performance energy benefits, and benefits are higher at low temperature. It's low cost and low complexity. But of course, like with any idea, you need to determine the reliable operating latencies for different temperatures. So this leads to higher testing cost. Clearly, its higher testing cost is not good for cost in general, but it's not that bad, I think. Now, if you want to get rid of some of the reliability guarantees, meaning if you know your application data, you can exploit this idea in a different way also. You can reduce the latencies, get some bit errors, and you can map your data that can tolerate some of those bit errors to those parts of the DRAM device that lead to some errors. Okay. Basically, you can do that also. I'm going to talk about it. And we have a paper coming up at Micro that talks about, so you have a neural network application that you know that's tolerant to different error rates, and different parts of the network layers are have different levels of tolerance. If you reduce the latency and reduce the voltage, you get some error rates in your DRAM device. Now the key question is, how do you optimize the performance and energy of the neural network inference by mapping the different layers to different parts of the DRAM device so that you can get high accuracy at the same time. So this requires you to get the error models from the DRAM, which you can get with what we've done because we have real infrastructures to get the error models. Feed the error models into the training procedure you have in the neural network so that you maximize the accuracy, and then do the mapping nicely. I'd be happy to talk about that separately, but once you have an infrastructure like this, you can actually enable a lot of interesting ideas. Okay, so this is the paper. Now, this Adaptive-Latency DRAM exploit latency variation across time and across chips. Then the next question we asked was, is there also latency variation within a chip? And the answer is yes, obviously. I'm going to talk about that. So this is one example. Once you reduce the activation latency by some amount, this is the error patterns that you get in a DRAM subarray. These are the rows, these are the cache lines. Actually, this is the DRAM bank. And this is the probability of a cache line having more than one bit error. And you can see that most of the cache lines don't have errors. Errors are localized over here, and they're concentrated in certain columns. So if you know this sort of spatial variation information, you can expose this to the memory controller, and the memory controller can use different latencies to access different locations. That's the basic idea, a very simple idea in the end. And this paper has a lot of analysis of real DRAM chips to show how these errors happen in real DRAM chips. Okay, so basically it's a software transparent design that reduces latency. It's called flexible latency DRAM. You divide the memory into regions of different latencies, and the memory controller uses lower latency for regions without slow cells and higher latency for other regions. And you can see that these are actually profiles of three real DIMMs that we found out using our infrastructure. So this DIMM is actually very strong. If you reduce the activation latencies to 7.5 nanoseconds, 99% of the cells work correctly. For less than 1% of the cells, you need to reduce it to 10 nanoseconds, and you really don't need 13 nanoseconds, which is the standard latency for any of the cells. This DIMM is less strong. The DIMM is even less strong, as you can see. Basically, there's a distribution of reliable operating latency across different cells in a DRAM chip, and you can exploit that to reduce latency by adapting the latency parameters to the cells. It's very similar to refresh rate adaptation to different retention times across cells, right? So this is the upper bound. Everything is accessed with 7.5 nanoseconds. Now, exploiting this real data, we did a lot of simulations to understand how much performance benefits you would get if you had a memory controller that exploited this phenomena. And basically, this is what we saw. This is the upper bound. The upper bound is about 20%. And we get very close to 20% in this DIMM that has more than 99% of cells that can be accessed at the upper bound, lowest latency. Of course, DIMMs that are less strong, you still get a lot of benefits, basically, because you can get rid of the most of the latency in most of the cells. You may not be able to access them at the lowest latency, but you can access them at the intermediate levels of latency. So that's the idea. It's a very simple idea. There's a lot more analysis in the paper. This paper actually has a lot of observations on real DRAM chips, but I'm not going to talk about them since we don't have time. So this idea reduces latency significantly. We call this fly DRAM, flexible latency. You're more flexible in the sense that you're adapting to the latency within a DRAM chip. So we're exploiting within chip latency variation. But of course, you get even more testing cost now. You need to determine the reliable operating latencies for different parts of a chip. And this leads to higher testing cost, even higher testing cost. I think overall, this higher testing cost is not good, but if you have an intelligent memory controller, the intelligent memory controller can actually do this testing while the system is running. Initially, you start out with high latencies. Over time, you figure out some regions of memory can be accessed faster and faster. Now you build a profile of latencies of your DRAM chip, and over time, your computer becomes faster, actually. I think this is a good thing, probably. People should be marketing this way, probably. A computer that's becoming faster over time. And I think over time, you really need this profiling in the memory controller, because if you determine these latencies during manufacturing time, you have to put some margin. Even in our experiments, we put some margin, because you don't know what will happen 5 years down the road, right? There are aging effects that you cannot really take into account when you're profiling at that point in time. But if you're doing this profiling once in a while in the field, you're really taking into account all of those aging effects, so you can really adapt to what's happening in the environment and in the system and the workloads. So it's a much better way. Having an intelligent memory controller is a much better way of specifying these latencies. You can cut down a lot of the unnecessary latency that way. So basically, you have a slightly more complicated controller if you do the profiling, but you also need to have a slightly more complicated controller so that you can store what latency parameters you should use for different parts of a DRAM chip. So if you're interested, this paper has a lot of ideas. Yes, please.
So you cannot actually do this yet with like stuff that's on the market, right?
That's an excellent question. The answer is no. You can do it in an FPGA-based memory controller, actually, if you design your own controller. So the answer is yes for FPGAs, but not general-purpose processors, no. Actually, some general-purpose processors have mechanisms to change the latencies in the memory controller dynamically. They're not exposed to users. We've been working with some of those, but they're not exposed to general users at the moment. So it's not actually it's not hard to do this, add the support in real systems going forward. People just need to do it. Yes? How
granular are the sections of the memory that are, or that it present the same latency? So that's one question. And
okay, sure. So we have a lot of analysis in the paper. The granularity varies. For example, some banks are faster, some banks are slower. Some of them is coarse granularity, some of them are fine granularity at the row level and the column level. So I think if you add more complexity to track different granularities, you get more benefit over time. But the controller becomes more complicated, of course, right? Yeah, that's a very good question. We actually have another paper called Solar DRAM. I like the name of it. That talks about a lot of that granularity issues, if you're interested. Okay, so maybe I'll cover this one, and then we'll skip the rest of latency, and then we will conclude, since I don't have a lot of time. But these are very good questions. Or maybe we spend time in questions. What is people's preference? More questions, more material? I'm done. You can go. Is that that's also possible? Okay, let me give you this one very quickly, because this is, I think, a cool idea. This is actually a paper that does this, proposes dynamic profiling of latencies, and it has an idea. The idea is basically there's a design-induced variation in latencies. If cells are far away from the sense amplifiers, they're slower. If cells are closer to sense amplifiers, they're faster. By nature, chart sharing is very fast over here. Across the column, if cells are close to the word line driver, they're faster. Farther, they're slower. So clearly, there's an inherently fast region of memory because of the way architecture is designed, and there's an inherently slow region. And the idea over here is if you know this inherently slow region, you can profile only that region, and that region tells you what is the latency that you should access this particular subarray with minimum reliable latency, because the hope is that everything else is stronger. Okay, that's the idea basically. Of course, I'm going to embellish this idea a bit. We profile only the slow region, so profiling is really fast. Of course, now you need to know where that slow region is. Somebody needs to provide that information. It's very similar to the Rowhammer solution, right? Somebody needs to provide where these cells are. You can dynamically try to discover this, but it's not very easy also. And the paper that we've written actually has a lot of reverse engineering results. You can take a look at them. But of course, life is not as nice. Life doesn't give you only systematic variation. Life gives you random process variation as well. So some cells are slower randomly. So you need to somehow profile them as well. So this is actually very nice for, this is random. As a result, what we do is, to tolerate these random errors, we use ECC. So if you want to actually profile the errors, you get errors when you reduce the so you figure out the lowest latency to access memory with by profiling this region. Some cells are not happy with that latency, so they get errors. You catch those errors with error correcting codes, and turns out these cells are randomly distributed, so simple error correcting codes work well. And once you catch those errors, you increase the latencies. That's the idea. So we basically have an adaptive system that figures out the latencies by a combination of online profiling as well as error correcting codes and back off when you get errors. And if you really want to know more, the paper has a lot more detail, and these are real results. So basically this is adaptive latency DRAM. As I showed you, it's good, but if you do this profiling online, you get much better. Because adaptive latency DRAM, again, it doesn't take into account aging, but this takes into account aging. You could keep doing this dynamically, and you can actually adapt the error correcting codes to get even higher benefits. And write latencies are usually better to reduce. So one downside of adaptive latency DRAM is at high temperatures it doesn't reduce latencies that much. We fixed that problem basically. Now we're temperature independent in terms of how much we can reduce the latencies. Okay. So the big advantage of it is, we can automatically find out the lowest reliable operating latency at system runtime. The dynamic profiling mechanism. And it reduces latency more than prior methods because it takes advantage of ECC also. It reduces latency at high temperatures as well. Now, of course, you need to have this information, but I think going forward we really need to expose more information about the DRAM chips. You can reverse engineer this information with a lot of effort. Actually, you can build a memory controller that figures out this information as much as possible, but I think it's really a waste of time to do that, unless you're launching a security attack, of course. If you're launching a security attack, by all means do that. Actually, security researchers are the best researchers to reverse engineer these structures in general, because they really need to know what's adjacent. Okay, it requires ECC, but ECC already exists in existing chips, and it imposes overhead during runtime profiling, and you really want to minimize that. And this is a paper that talks about it. If you're interested, you can read it. Now, unfortunately, since we don't have a lot of time, I'm going to not run through these slides because there are a lot of slides, but there's more material basically if you're interested. So this is very interesting also. I'd recommend you take a look if you're interested. And our upcoming paper actually exploits the voltage latency reliability relationship. So this is one example I'll show you. Since you asked that question, what is the granularity? This shows nicely. When you reduce the voltage, you get some errors that have no errors, some banks that have no errors, some banks that have a lot of errors. And even within the banks that have a lot of errors, you see that there's some variation, right? Granularity is at the row level over here in this case. So you can take advantage of this also, because errors concentrate on some regions. So I've already talked about the PUF, you can take a look at it, and the random number generator. I think these are fascinating to me, but unfortunately we don't have time. Let me see what else I would like to tell you about latency in the last 22 minutes. Or you can ask a question. Okay, no questions. So let me give you an architectural idea to reduce latency. This is something that we've published recently. We've done a lot of work on microarchitecture, DRAM microarchitecture to reduce latency. I like this one because this is a very general substrate. Let me give you the idea. So we wanted to tackle multiple challenges at the same time. And if you look at conventional DRAM, you've already seen this. This is a DRAM subarray. Basically, you activate a row and the data comes into the sense amplifiers. So my student Hassan had this idea to divide a DRAM subarray into two portions. One is regular rows and the other is copy rows. Copy rows can store a copy of one row here. Let's take a look at how you can use this. Basically, this exposes two primitives. One is row copy, which brings the data from here to sense amplifiers, from here to here. You know this. This is very similar to row clone, basically. Now the difference is we have different decoders over here. This is a regular row decoder, and this is a crow copy row decoder. This is very simple because now they're partition decoders, so you don't really have two decoders covering the entire space of the subarray. You have two independent decoders. Now you can activate this one and activate this one and then accomplish a copy, which means that you copied the entire row here and here. Okay, we're going to take a look at how to take advantage of it. Now if you've copied this row's contents to this row's content, the next idea is you can activate both of them at the same time. Now if you do that, because you have the same content, you have a lot more charge driving the sense amplifier, so the activation is much faster. That's the idea. This is dual row activation in this case, but you could, the idea is more generalizable. Of course, dual row activation is simpler to implement than triple row activation, ... So that's the idea over here. So we actually show a bunch of use cases on this one. Crow cache, it reduces access latency, exactly what I described. Whenever you access a row, you copy it into the copy row, and the next time you access the row, you activate both rows. So of course memory controller keeps track of which rows are copied, and it can actually reduce latency for rows that are copied over here. And the second one is, now if you can copy a row from here to here, you can get rid of refresh on weak rows. So if you somehow figure out this row is weak, you can copy that row to the strong row and remap it in the memory controller. Memory controller, whenever there's an access to this row, memory controller actually accesses the strong copy of that row. Now you can reduce the refresh rate for those rows or for the entire DRAM. That's the idea. And also there's a mechanism for protecting against row hammer, because if you figure out that some rows are being hammered over here, you copy them over here so that you can get rid of the hammering issues. I think there's more to be discovered over there. That's why I'm not going to talk about it. But basically, if you use a substrate that looks like this, it's very low area overhead. You need to have some memory controller changes. This is again another example of overcoming DRAM scaling challenges by designing memory and controllers together. You get significant speed ups and energy improvements. And if you're interested, this is one of the latest works actually on reducing memory latency. Now I don't have time to cover this, but this is really one of the first works that we've done when we started looking into DRAM scaling. Okay, let's see where we are. Okay, I think I already talked about a lot of these. How about we go to the last slide? I have a lot of other slides over here, but I think I'll make these slides available, and I assume you'll post them somewhere. Okay. Okay. So this was the study that I was talking about. Basically, this is I don't know why this is going backwards, because I'm making this is I wanted to conclude basically more motivation to reduce memory latency. And it's really about the workloads in the end. Software wants low latency. We wanted to do this study where we examine the new DRAM types and the effect of new DRAM types on applications, and we did a lot of experiments actually. This is actually an interesting story, because when we submitted this work to ISCA, we got the comment, you should do the study on a real system. And clearly there's no real system that can support more than one memory type. So you really cannot do the study on a real system. I think people should have known better when they gave that comment. So you really have to do the study on a simulation, because we really studied 9 different DRAM types and more than 100 different workloads. Basically, these were the DRAM types. You can see there. Actually, this paper covers a lot of DRAM types. If you want to learn about DRAM, that's LPDDR4 is there. It looks at a lot of different trade-offs in DRAM design. And one of the conclusions is basically you want lower access latency to get performance. Basically, new DRAM types often increase access latency, but many applications cannot make up for that increased latency in the end. And basically, the key takeaways in this work is 4 things. DRAM latency is a critical bottleneck. Bank parallelism is not fully utilized by a wide variety of the applications that we examined. So you need to rewrite your application sometimes. Spatial locality is still important. Maybe this is obvious. But the memory subsystem needs to exploit. Some memory types actually reduce the spatial locality, and they actually lose performance in many cases. And actually, low power memory is very promising, but its latencies are sometimes too high. So if applications are tolerant to latency, they could be promising. Okay, I said I'm not going to cover, but I did cover. Okay.